Okay, welcome back, everybody. And a new session in Physics STK 4155. The topic now is part one of us setting up the machinery which is needed to write a code for neural networks. So project number two is going to rotate around that topic. And as you've seen from the lab sessions, we've been discussing how to calculate gradient descent and implement gradient descent methods. And this is something which is going to be needed when you're setting up the second project. And then after we've done with the gradient method and implementations and testing of that, then we are going to move into writing a neural network code. So today, we are mainly going to do a standard whiteboard lecture, where we're going to go through the details of a neural network. And we're going to set up the basic algorithm for training the unknown parameters. So now we're actually changing from what we have done with linear regression and logistic regression, where we have a deterministic equation, which gives us simple expressions or expressions we can solve numerically for the optimal parameters. Now we are actually going to set up an algorithm where we train so that at the end we have the optimal parameters. And the training is done by an algorithm which is called backpropagation. So I'm actually going to switch pretty soon to the whiteboard here, and we are going to go through many of these gritty-nitty details. And we are going to set up the backpropagation algorithm, which is nothing but you using the chain rule for derivatives. That's the demystification of what the backpropagation algorithm is. Next week, we will discuss how to program it. And during the lab sessions next week, we will also discuss the link between backpropagation and automatic differentiation. Because at the end, to make life simpler, we are going to have to deal with lots of derivatives, and the best way to deal with them is actually use automatic differentiation, because it's so easy to interchange some indices, and interchanging some of the indices may often lead to wrong results. So we are going to express everything now in terms of what mathematically are called affine transformations. This means essentially that we're going to have matrices times vectors. And the basic mathematical operations which we have are matrix vector multiplications and matrix multiplications. Okay, so these are the basic mathematical operations combined with us calculating gradients and setting up the derivatives, which means the expression for the gradients. Okay, so what I want to do now is just to start with the kind of overarching view of the elements which we need to have. So I'm going to switch to the whiteboard here pretty soon. Okay, so neural networks. I'm going to use an acronym for NN. So this is our neural network part. So I should put an S here just to indicate that this is plural. And there's a long history, and the first networks were very much inspired by neuroscience. So you could actually think of you sending in a signal, and then the signals get modulated according to voltages or whatever, and then you get an output. But let's just set up the basic elements which we are going to need. So this is part one. And these are the basic equations. So one central ingredient is the so-called universal approximation theorem. And I'm going to set that up a little bit later, but now I'm just going to mention it. So what this theorem says in words is that you can approximate a continuous function, which is not necessarily linear, with a neural network which has at least one hidden layer. So that means that you can approximate a given function to a given error by setting up a neural network with one hidden layer. And that function is continuous. The original version was done by so-called sigmoidal activation functions. But then Hornik in 91, after Sybenko, or Sibenko, I think he was Russian, or is Russian, in 89, formulated the original theorem. Then it was extended to functions which are bounded, but non-constant. And we are going to come back to this. But the theorem is extremely powerful. And it says that with one hidden layer, you can actually approximate a non-linear function to a given approximation. So whether you get the exact one is something you don't know. But the theorem claims that you can actually approximate a function which is a continuous function. This is going to change a little bit things. So what we are going to look at now are the components of a neural network. So clearly we need, one thing we need is a cost function or an objective function as before, a loss function or risk function. I'm going to use cost function in general. So we need that. And this could be the mean squared error or other types of cost functions. So you have to decide on how you want to model the data, okay? So this is something we need irrespective of whatever we do. And then you need also functions to assess the quality of the fit you made. So the cost function is the one where you have all the unknown parameters and you optimize this function in order to find the optimal parameters. So this is as before. Then nothing changes here. And you can, when you have made the fit, if you're doing a regression problem, you could then set up the mean squared error, the R2 score, the relative error, depending on the kind of error you think is the most relevant for the data you have. So this doesn't change. Now, what changes, however, is that now your model is given by the architecture of the network. So the architecture of the network, architecture of NN, of neural network, that is something you should read as the model. You still have the data, you still have the inputs and the outputs, but now, instead of you making a polynomial fit, you're going to set up a neural network, and the architecture of that one defines your model. So this architecture will contain the following elements. And these are things which we're going to define a little bit later. It's going to contain the number of hidden layers. And I will come back to why they're called hidden. It's going to contain the number of nodes in a hidden layer. So I'm going to use the word nodes. Some people use the word neurons because neural networks were very much inspired by neuroscience. And then you would typically have a neuron which gets a signal or many signals, and then it sends an output depending on the signals. So that means that the neuron or the node or unit, you will often see that these names are used interchangeably in the literature. They have a function which then modulates in some way the data you send in, and it produces an output. So this modulation function is normally called an activation function. So let's put this up. So your number of nodes in hidden layer. And you can have different hidden layers and a different number of nodes in each layer. So we get the next term, which is C, and that's the type of activation function. And I'm going to label this with a sigma. Originally, it was intended to be the sigmoid function. And this has an input z, which I will come back to. Now, there are tons of activation functions which you can use. That becomes actually a parameter in your model. So the sigmoid function was widely used till people realized that the sigmoid function led to gradients which could disappear or which could explode. And that stopped the training of a neural network. So in the literature, we are also going to meet many different types of activation functions. I will come back to how you can think of an activation function pretty soon now. I just wanted to set up what defines the architecture of a network. And the architecture is your model. So when you're looking at the complexity now, the complexity could be, instead of a polynomial degree, it could be the number of hidden layers you have. That would define the complexity of your network. So when you've done that, you need more. You need an algorithm for finding the derivatives for training. So this is the back propagation, which is nothing but the chain rule for derivatives. And as you will see pretty soon in the next lecture, for setting up the gradients. For training. So the back propagation is the way by which we train the network. So this is an algorithm which we are going to derive and set up, and you would have to implement that in your code in project number 2. Then the next ingredient which you need are different gradient methods. So you would have the whole family of gradient methods for training. So the back propagation is just an algorithm which gives you the expressions for the gradients. So when you have the gradients, then you need to implement them numerically in one way or the other. And then you would need some of the gradient descent families in order to perform the training. Gradient descent, gradient methods for training. And this could be plane gradient descent. It could be a stochastic gradient descent. So I just write this as GD, SGD, etc. So these are things which you now, in the first exercise for the project, you're going to set up this family of gradient methods. And as you've seen with these gradient methods, you need an expression for the gradient, because else you can't do anything, okay? And finally, you have all the hyperparameters. And there are tons of them. So this is lambda in a term like lambda, where you now make a sum of a j of beta j squared, which we have had no, not that way, but this way. I have a beta j squared, etc. We have the learning rate, which is a hyperparameter, which enters the gradients, learning rates, etc., etc. So depending on the type of activation function you have, some of these come with parameters which you can tune. But the two main parameters, those which affect the results the most, are actually the learning rate and this hyperparameter lambda. So you will often have a cost function which includes some kind of shrinkage term, in the same way as you did with lasso and ridge. So these are parameters or additional terms in the function you want to optimize, which are normally included routinely in neural network calculations. So this is basically the overarching thing. So when you now, in project number 2, when you are going to fit, let's say, the Franke function, you are not going to send in a polynomial to the neural network. You are just going to send in the x and the y data and the z data as output. And then the network will find the optimal description of your data. If you send in to a neural network a design matrix which contains a polynomial approximation, then the neural network will try to fit that polynomial for you. And that may not be the function you want. So if you feed in a 5th order polynomial in the design matrix, and your data is given by a 10th order polynomial, the neural network will try to fit a 5th order polynomial for you, the best possible way. So in a neural network, you would just send in x and y for the Franke function as an example, and then the neural network will find the best representation for you. So when you're setting up the model now, the model is given by the architecture of the network. So I think it's important to keep these differences in place, because sometimes one may be tempted to just take what you did in project 1 and just feed that one into the neural network. But that defies, in a way, the whole philosophy of a neural network and the universal approximation theorem, which says that you, with a given architecture and one hidden layer at least, you can fit a continuous function. Okay, any questions so far? Does that sound clear? Good, yeah? Yeah, tuning hyperparameters, yeah.
Yeah, was they included the cost function?
No, the cost function is something you decide upon before the training. Because the gradients will be defined by your cost function. So this is the same as you did with linear regression when you had ridge and lasso. You defined the function you wanted to optimize. So in a certain sense, the cost function becomes also a model which you make up. Okay? So these are the basic things which we are going to discuss again and again and how to implement. But let's now look at some simple cases. And in order to introduce the basic notation. So let's take a graphical representation. And this is often very convenient. So if we now look at a simple network with just one node, this is called a single perceptron model with one node and no hidden layers. So there are no hidden layers now. So the way you could think of it, and this is what we have done till now, you have some input x of I, and then in here, you have some function f of x of I, and that gives you an output y of I. So you could now say that this blob here, or this circle, is a node, and it receives an input. This function f of x transforms the input into an output. And the whole field is very much inspired by the way neurons are functioning. So neurons get electrical signals, and then the signals can be amplified or they can be reduced by the neuron, and that ends with a final output from the neuron, which then can be sent to other neurons. So that's the way you typically communicate information in your body, by the way. So as an example, let's now look at a simple case here. So this is the simple perceptron model. So we could still have two inputs here. We have an x1 and we have an x2 here. We get an output, which we simply call for y. And then we have a function here, f of x1 of x2 here. So this is a function of the two variables. So one type of simple case we could make is now that this y is given by x1, and then there is a simple parameter, w1. And x2 is, you can think of the x's being modulated by some quantity w plus some quantity b. So this b, if you think of a line you're fitting, that could be the intercept, just to give you an example. But I'm bringing this up because we are going to define new sets of parameters. So we are going to call these parameters here for the weights. And this parameter here is something we will call for the bias. I will come back to why they have these specific names, but you can now think of you having a function which modulates your input, and it scales them with some factor W and 1 and W2. There is a bias, which could be some external signal which comes in, which conditions the final output, and then you have a final output. And again, just think of a straight line. You're fitting a line. So a simple case we can look at now, which illustrates a little bit of this, is what in electronics you call an OR gate. And you may have heard of that. So let's look at the explicit example, which is called an OR gate. And that's a pretty simple case. And we can be tempted to fit a straight line in order to reproduce the data. So this function which we have here, that has, you will often see it depicted this specific way. So you have a bit 1 or bit 0. So you have an input x1 and an input x2, and you have an output y. And I'm going to put a new label for that from here and on for T for target. So the target is now the output value, and this is the value we are targeting. Okay? So I'm going to use T for the values we want to reproduce from now and on. This is pretty common in the neural network theory. So the OR gate, we can now set up a table here with x1 and x2 and T. And you've probably seen this. So if you have 0 and 0 bit and 0 bit for x1 and 2, this gives 0. So that feeds the output 0. If I have 0 and 1, since it's an OR gate, it gives either 0 or 1. So this gives 1. And 1, 0, 1, 1, and 1 and 1 here. Okay? If you make a graph now, you can make a plot of this. These are discrete values. But since we are pretty obsessed with linear regression, we could now think of making a fit here. So I'm going to put the zeros as closed circles. So this is just 0. And then I have 1 as open circles. Okay, suppose now that I have been so good in convincing you guys that linear regression is the only thing you can do. And that's the best thing to do. How would you use linear regression here to figure out whether you get the 0 or 1? What could you do here? What is the simple thing which comes to your mind to separate the zeros and ones? Any good suggestions? So I want to, in a way, classify, but I am obsessed with linear regression. So I want to make a fit to the data here. So if I make a fit, what could that fit look like? What could it look like? The simplest possible fit you could make here in order to distinguish between zeros and ones. Any good suggestions? Yeah? A straight line. So I could fit a line on the data now where I simply do this. So if I can find that line, I would say what's above is 1 and what's below is 0, right? That's the simplest thing. And I could actually use linear regression here in order to make that. It's not the best way of doing it. It's actually not very smart because you can have tons of lines which go through it. So there are lots of solutions, but let's see how that works. So this is going to also allow me to introduce some new quantities. So suppose now I want to make this simple fit. So I want my that specific function now to my optimization problem to actually fit this case here, plus b equal to y. So this is my model. I define now a vector wt, which simply contains w1 and w2. And then I have an x transpose, which contains x1 and x2. And then I have this bias parameter. So my y now can be written out in terms of the inner product of these two vectors plus b. And this is now the function which I want to try to approximate, to fit with the data which I have. Now, if I look at my data then, my x of t, that has my x of t here could be given by 0, 0. That's one value. I could have 0, 1. I could have 1, 0. So these are the bits which I can feed in. And then I could have 1, 1. Then I'm now going to use a new variable, which I call for theta. And that's going to be a collective container for the weights, the unknown weights, and this bias parameter. And I'm going to write this theta as a vector now, which contains b, w1, and w2. So I'm simply now, since I've been so good at indoctrinating you guys about linear regression, I'm just trying to apply linear regression to the problem. So this will be my vector beta, which we had before. But now since the variables are different, I have the weights and this bias parameter, then I want to make a distinction. So I just introduce a common variable theta for all the parameters we're going to train in the network. Okay? You can then set up the design matrix. If you go back to this one, then you know that, okay, the b's have to be equal, have just to give ones. And then my x1s have to define this column, and x2 has to define that column. So I could simply now set up my design matrix as before. So I would now define x in terms of ones. So this would be the bias. And then I have x1, which comes in here. 0, 1, 0, 1. So these are my x's. I can then easily calculate and invert this matrix, which now simply becomes, if I done things correctly, 4, 2, 2, 2, 2, 1, and 2, 1, 2. I can invert it, and I can get my theta, the optimal parameters, which are just given by x transpose minus 1 times x transpose times y. And y is the target. So this is the quantity which we label as a t. And this t as a vector is given by 0, 1, 1, 1. Okay? So I know this, and I can calculate it, right? So if I run the calculation, let me just give you the results for it. So what you will get then is for these parameters theta, you will find that the optimal ones, when you just perform this matrix inversion, then you get 1 divided by 4, 1/2, and 1/2. And then you will get that your model, y tilde, which I label for y here, is given by 1 divided by 4, 3 divided by 4, 3 divided by 4, and then there's another 3 divided by 4. So this is y transposed. Now, take a look now. So what you have done is to fit a line, okay? So what this fit of the line gives you are 3 values which are the same and 1 which is different. But you want this, right? That's what we want. We would like this fit we made to give 0, 1, 1, 1. It doesn't do that because we're just fitting a straight line which separates the domains. So how would I use these results? So, yeah. Say it again. So what you could do now, you would use a step function, and what you could say is that if you look at the results here, if this y less than 1/2, then y is equal to 0. If y larger than a half, then y is equal to 1. Because the only thing I did now was just to set a line, and that line gives me values. So I would then say that if I am below 1/2, then 0. If I am above, it's 1. And you see now I have three values which are the same, and they should correspond to this value. And then this 1 divided by 4, which should correspond to the 0 value. Because the only thing I do is find a straight line which separates the two possible outputs. And then I have to, as you said, I have to set up a step function. If the value is below 1/2, 0. So I can actually, with this simple model, I can fit this data. Yeah? No. So you see now, I can have a simple model without any hidden layers. Let me show you another gate. There is a famous gate, which is called an XOR gate. And that has a different type of result. So we are feeding in x1 and x2, and we get an output. So if you have 0, 0, gives 0. If I have 0, 1, it gives 1. If I have 1, 0, gives 1. And then I have 1, 1, it gives 0. Now let's make the plot again. So when I have 0, it gives me 0. And if I have 1, it gives me 0. And if I have 0 and 1, it gives me 1. So I have 1 here and 1 here. Can I fit a straight line to separate these variables? So suppose now you are even more indoctrinated by me, and you think that fitting a straight line and linear regression is black magic, which solves all problems. Could you apply the same thing you did for the OR gate here? You can't do that, right? You see that immediately, because what you see here, okay, I fit a line, okay, I can fit this line. It doesn't do the job. You can fit whatever line you want with whatever slope, but you would never be able to actually make a fit. So if I insist on my linear regression, what I would get as prediction now, if I do my standard linear regression, as we did with the OR gate, if we do that, we are going to make a prediction y, which is equal to 1/2, 1/2, and 1/2, which sounds reasonable because it just goes in the middle. Whereas what you want is 0, 1, 1, and 0. So you see now that this kind of fitting this one in with a linear function doesn't make a job. Actually, a simple node, as we put it up, leads to this type of fitting with a simple function. So what we need in order to fit this case, we need a more complex function. So what you can show is actually you need a neural network with one hidden layer to fit that. So in the example which we had, you can view what we put up here, this one. This is a neural network with one simple node. You have an input, something happens here, and then you get an output. So this is normally called a neural network without a hidden layer. So hidden layers means that you have an input layer which feeds in to some complex functionality in the middle, and then that spits out something for you. So in this case, we are just feeding in directly into a function which we may know, and then that spits out an output. And in this case, we can actually not use that simple model to fit this XOR gate. Actually, you can fit this with a simple neural network with one hidden layer and two nodes. Then you can fit it. And we will see that later when we have implemented a neural network code. So we will come back to this example here. Any questions so far? So the hope is that when you see this kind of graphical images here, you can intuitively see that, okay, if I would insist on fitting a straight line without any complexity, this is not going to do the job. And you see that graphically. And then when you run the numerics with a standard ordinary least squares, you just get crap. Okay? So what I want to do now is to start looking at the neural networks. And I wanted to say a little bit about the this theorem. So typically, when the basis for neural networks is the universal approximation theorem, which says that you can approximate to a given error any continuous function. And this is extremely important. So any continuous function with at least one hidden layer. So that's the universal approximation theorem in a nutshell. This does not mean that the network can be used to exactly compute any function. It only computes the function to the approximation that is as good as we want. So what the theorem says, so let me just quickly state it here. So we are not going to prove it. That's an exercise in real analysis. So there is a paper by Sabenko. And then there's another famous paper by Hornick back in '91. So what the theorem says is that if you have a given function, and this is normally defined on a d-dimensional cube. So this could be a function in a multi-dimensional cube which takes values between 0 and 1. So it's just normalized to 0 and 1. And you define a parameter epsilon, which is larger than 0. Then there exists or there is a one hidden layer neural network so NN is neural network, which now has parameters f of x and these parameters theta. So it has an input x of the form with this theta now contains some weights which link the input layers with the hidden layers and the nodes there, and a parameter b, which is called the bias, where w is typically a matrix of dimensionality n times n, and this b is a vector of length n, for which we have that f of x as a function of these parameters theta minus f as a function of x is smaller than epsilon for all x in the same hypercube of dimension d. So this simply says, I mean, if you think of the Weierstrass theorem, if you're familiar with that, that's a similar theorem you would use for polynomial approximation. If you're using Fourier expansions, you would have a similar requirement on the error you make with a Fourier transformation. Are you familiar with Fourier's theorem? So if you have a periodic function, you can approximate a periodic function with sine and cosines. And you can actually, in principle, this is an infinite series of sines and cosines if you have a periodic functions, but you can approximate it, and that approximation error is something which pertains to Fourier series. And the same thing is here. This was extended by Hornick to apply for the functions which are not sigmoid-like. and which doesn't need to be constant in certain limits. So when Sibenko did it, this applied to activation functions, which had a limit 1 when x went to this input went to infinity, and 0 when it went to minus infinity. Then this was extended to any type of activation functions by Hornig. So it's an extremely powerful theorem, and that's the one which promises that we can actually, by training a specific network, that we can actually reproduce a specific complex functions, which may be very difficult to reproduce by standard polynomial fit, as we've done in linear regression. So neural networks, they promise a lot, and then it just remains to see if they do that. So the class of functions which can be approximated are normally the continuous ones. So if the function f of x is discontinuous, it won't in general be possible to approximate it. However, the network may still give a decent approximation to that function where it is continuous. So you don't know that before you've tested it. And one of the things you will typically do with neural networks, like you did with the polynomial fit, is to change the architecture. You would change the number of hidden layers, you can change the number of nodes, you can change the activation functions, etc., etc. So that means that in essence, you're going to run many numerical experiments with different architectures and inputs, okay? So this is, sometimes it's a little bit, how to say, not pleasing, because it means that you have to run many numerical experiments. So when you run neural networks, think of that as a numerical experiment. And many experimentalists, they just say, okay, let me try this one, let me try that one. And then if the experiments can run quickly, you would try many options. But often when you have a deep network, it takes a lot of CPU time to actually have the network trained properly. Okay, so that was a little bit about the basics or the surrounding basics. So what we are going to do now is to jump into the back propagation algorithm, because that's going to be the backbone of what we will be doing. Propagation algorithm. So if we look at a neural network, and we do this in a graphical way, which is often very convenient. So then we would have an input layer. And then this feeds in to a series of hidden layers. I'm just going to write this with dots in between here. So this would be hidden 1, hidden 2, and then we have a hidden, let me just make these circles a little bit larger here. This is a hidden L, and then this ends up with a hidden L, which is the last one, which is the output layer. So that produces an output, which I now will label with Y. And this is then confronted with the target. So this is where we have the, let's say the mean squared error or the cost function, which we want to optimize, etc., etc. So this is where we confront and test the quality of what the model produces. So this is now fed forward like that. And this neural network contains a feed forward stage. And then it contains a back propagation stage. So in the feed forward state, when you initialize the network, you would have some initial values for the unknown parameters, these W's and these B's. Then you would send all the parameters through the network and produce an output. Then, when you produce the output, you compare that output with a target value. Based on these target values, or the outputs you have, you compute gradients. And then you go back and train the parameters till you reach the first hidden layer. Now you have updated the parameters, and then you do a new feed forward. And then you go back and forth till that cost function you have defined reaches its optimal value. So if the cost function is the mean squared error, you would train back and forth till that mean squared error has reached an ideal value, which ideally is 0, or a value which you are willing to accept as a good value. Okay? So every iteration of a neural network consists of one, a feed forward pass. You produce a new output. You go back, you train the parameters by gradient descent. And then you start again. So that's one iteration. And then you go back and forth. And you have to accept a certain number of iterations. You have to define how many you're willing to accept. And then you would go back and forth till you reach, let's say, an optimal mean squared error. So this is essentially the training you would perform. Now, what you see here, which is different from the training you would perform in linear regression, is that we don't want to drive the gradients to 0. Because in the back propagation, if I train the gradients to 0, the training will stop in a back propagation stage, and you will see why. So that means that vanishing gradients is something we don't want. So what we have as a target is the final, let's say, mean squared error. So after the break, we are going now to look at the structure, at the general structures, and we are going to open up this object here, and we are going to set up the mathematical elements which we need in order to use the chain rule and find the gradients which need to be used in the training. So in general, everything we do here, from the input to this layer, is going to be represented by these unknown parameters, the weights and the biases. And we are going to rewrite everything in terms of matrix vector multiplications and matrix multiplications. So these are going to be dense matrices because we are going to connect all the nodes in one layer with all the nodes in the next layer. When we come to convolutional neural networks, we are going to try to minimize the size of these matrices by some smart transformations or some smart filters. But here, we are going to have dense matrices, and that means that also a neural network becomes heavy to train unless we try to simplify the density of these matrices in some way or the other one. So this was about the overarching structure. And after the break, we're going to look at the gritty-nitty details of how we set up the back propagation algorithm, which is the way we train the network. Any questions? Is it pretty clear what we want to do? So the philosophy is very different from linear regression, where we have a simple analytical expression to invert. So what we're going to do now is to go through the mathematical details of how we would set up a neural network. And this is going to lead to the back propagation algorithm. And this is the piece which we need to implement in order to have a neural network. So let's make a drawing now of the way we would implement the feed forward stage and the back propagation stage. So I'm going to set up a graphical display of a network with the different parameters. So we have the parameters we want to optimize are given by these weights, and I'm coming back to where they come from. So B, and the B is this bias. So these are the generic parameters. We are going to have an input layer. And that will have a series of nodes or neurons or units. We can give them different names here. And so we could have up to xn input data. So this would be x1, x2, etc. So just to give you an example, if you're looking at the of an image, an image has a given number of pixels. Every pixel would be one of these input nodes. So if you have an image with 8 times 8 pixels, 64 pixels, you would have 64 input nodes. So that's just an example on how you would define your input variables. And then these input nodes, they feed in to the first hidden layer. And I'm going to put a label on the hidden layers as an H of 1. And this has also a given set of nodes. So we could have a node which we are going to call. So let me just set up this one as an L, not that one, but this one. So this is layer 1, and that has a node H1, H2, down to some H, which we're now just going to call NL. And this has a 1 here, because this is layer 1. So the number of nodes in the hidden layer doesn't need to equal the number of nodes in the input layer. And this continues now to all the types of layers which we have. So we could have a layer L minus 1 here, and we have the different nodes down here. So this has a new node. So we're going to put a 1 up here and a 1 here, just to indicate that this is the given layer, L minus 1, 1, and this goes all the way down to H of L minus 1, and this has N of L minus 1 nodes, and this feeds in to the next layer, which we are simply going to call L. So we have a similar node here, and then we're going to pick a specific node, which we're going to call J. So this is Hj of L. And this continues all the way down to Hn of L, or layer L. And this continues till the output layer. So this is L, and I'm going to mark this one with the input. And this is going to be the output layer. So this is this one. And this one feeds into the, so this produces an output. And this output can be just one number. If you're fitting or you want to classify handwritten numbers from 0 to 9, you would have 10 outputs, each one representing the probability for number 1, 2, 3, 4, 5, 6, 7, 9, 0, right? So depending on the type of problem you have, you can have just one output, or you can have many outputs. Okay? So this produces an output, which I'm going to label for Y. And that is compared in a with a specific function with a target, P. So you feed in the target to this specific function, and you compare that one with Y. And this is how you compute the gradients, which you then use in the back propagation. So let's look now at this specific node here. So this specific node is now going to receive information from all the nodes in the previous layer. So all these will feed in to all the nodes here. And each one of these is weighted by a parameter. And this parameter is a parameter which we want to use a training to find the optimal value of. So if we now magnify, so this these nodes here feed also into all here. We would have the same here. They would also feed into all nodes, etc., etc. So all the nodes in a given layer are connected with the nodes in the next layer. However, the way we structure it in a standard neural network is that there is no crosstalk between the nodes in the same layer. So you could add that, but that would complicate the training. That would make it much more difficult. So if we now take and magnify this part here, then we're going to see how the things are linked here. So let's do that. So we have a hidden layer, which we are going to label as an L-1, and that has a set of nodes which receive information from the previous layers. We just mark that like this. And each one of these nodes is now feeding in to the next nodes, all the nodes in the next layers. So this goes down to n of L-1 of layer L-1. And then we have the next layer here. And then we single out that specific node J. So that receives an input from all these other guys. And the input now is going to be labeled in the following way. So this is layer L. So the input to this J in layer L is something which I'm going to label as a Z of J of L. Now this node is going to produce an output, and I'm going to label this output as HA of JL. So this is the output from node J of layer L. And this A of J is now going to be given by a function, which I just call for sigma here. And these are normally called the activation functions. So you send in some input, and then this function modulates this output in some way. And there are different ways of doing that. Now, in neural networks, since there are actually some constraints, because the derivatives and the gradients are going to be proportional to the derivative of that specific function. So when you define a function for these specific operations, the sigmoid function is the one which has been widely used. So let me give you an example for that. You want to have functions which are easy to calculate the derivatives of. So you have simple expressions for the derivatives. If you have complicated expressions, that will actually slow down your calculations. So there is a field which is called Bayesian machine learning, where you actually replace these activation functions with a probability distribution which you train. And that probability distribution is perhaps a better way of doing it, but it's much more expensive computationally. So the typical function which we would set up then, so this A J of L is now given by some function of C J of L, and the most standard one is the sigmoid function. Is much used, but we are coming back to other functions next week. And the sigmoid function, the sigma of C of JL, is actually given by 1 plus E of minus ZJL. So this is a function, when you plot it as a function of Z, what you will see then is that it goes to 0 when Z goes to minus infinity, and then it changes value and it goes to 1 when C goes to plus infinity. This is something which now clearly is a 1 when you look at it. It's easy to implement, and you could think that if the signal is below 1/2, you put the value to 0, and if it's above 1/2, you put it to 1. You could have used the so-called Heaviside function, which is just a step function. That's fully possible. But you would like to have functions which have nice derivatives and which are continuous functions as well. That's also one of the things you want to have when you're setting up this, because you're going to run this many, many times. So if you have 100 nodes in a hidden layer, which connect to 100 nodes in another layer, there will be 100 times 100 parameters. So you will have 10,000 parameters to decide upon. So this variable, Zj, if we now look back at the drawing which we had here, so this quantity here is receiving an input which then would be weighted by the weight function for layer L, which now receives a parameter 1j. So it receives an input from the first node here. So that is weighted with this parameter, which is unknown. It receives also inputs from W2 of j, and L stands now for the process which takes place in layer L. And then it would have terms which come from all these parameters, L minus 1 of j, etc., etc. So the way you would write this now, this parameter z of j, L, this is going to be given by a sum over all the nodes we had in the previous layer. So up to n of n minus 1, I have this weight matrix of ij, sorry, ij, and this is the weight function for layer L, and this is multiplied with the output from node I in layer L minus 1, and then there is a bias which comes in here for layer L. So that is a parameter. So this A, which you see, is the output from node I in layer L minus 1. That output feeds into that specific node in a new layer, and it's weighted by a parameter. So the training is actually trying to find the values of these weights, which are unknown parameters. So that means that when you set it up now, what you will see is that you would need this weight. This defines a matrix. So you can set this up in a matrix vector formulation where you have a Z of L, which is now given by this matrix for layer L. And this contains now a matrix which needs to be transposed the way we wrote it. And then it's multiplied with the output, which is now given in terms of a vector from layer L minus 1. And then it contains this bias from layer L. And sometimes I'm going to skip this parenthesis around the L's here. So you have a matrix W with unknown parameters. So W is a matrix containing the unknown parameters which we want to train. And B is a so-called bias. And the reason for that one is that sometimes you may actually get parameters W which become 0. And it's common to just fix the bias to a non-zero value so that in case this W becomes 0, there will still be an input to that specific node. So this bias is a way to prevent that the training can stop at a given stage in your training process. And this is a way you can view this bias. If we go back to this simple interpretation of a straight line, which we discussed before the break, you could then think of this bias as the intercept for a straight line. But here, it's going to function as a way so that you can hinder that by accident some of the weights are put to 0, because you would typically initialize your network with some random values for the parameters W. And some of these random values can actually be 0. And then the bias being non-zero will then include this node in the training. So it's common to actually include this bias in the training here. So what we also need to define is a cost function. So we need a cost function. And in the example here, I'm just going to use the mean squared error. So I'm assuming that I'm doing a linear regression case here, or a regression case. Here, the C of this theta and I skip the 1 over n. I just have a factor of 2 because when I take the derivative, the factor of 2 disappears. So I have a 1 to n, and then this is done for the last layer. And then I have my output, which I label as y, minus the target, which I label with t squared. So that is going to be my cost function. So in my previous case, when we did linear regression, I had a y tilde to indicate what the model gave. Now I'm just going to replace the output y with t for target. That's the value we want to reproduce. And the output of the network is just y. I hope it's not too confusing. Next, what I need now is to set up some quantities in order to perform the calculations. So in the back propagation, we are now going to set up the algorithm. So we have defined, let's just repeat the quantities. We have Cj of L, which is given by the sum of I equal 1, and then the previous layer of the outputs from the previous layers of L times AI, L minus 1, plus this bias for the specific node. I have the output from my previous layer, L minus 1, which is given by this activation function of C of I of L minus 1. I have this function, which I have defined now, this function of Z, which I will use in the examples here as a sigmoid function. So that's a typical function which is being used. And now I need some quantities, some help quantities. So some intermediate steps. And let's do this algebra. So I would need the derivative because I'm going to use the chain rule. So I would need a derivative with respect to some of these quantities. So if I use that one, you can now see that if I take the derivative of Z with respect to the weights, I would use this equation here, and then you see that I get this quantity. So that's the same as AI of L minus 1. I need another quantity in the calculations here. So these are just intermediate steps in order to set up the final algorithm. I have an L minus 1, and this is given by Wij of L. And you can see that immediately from the equation which we have here, right? So these are some of the derivatives we need. I need another derivative, which is a derivative of this function of L, of dzj of L. And if we assume that we have the sigmoid function, so let me emphasize that in examples here. That leads also to a computational note. When you're setting up the program, what can be useful is actually to make a class of activation functions and their derivatives. Because then you could simply set in an option saying that I want to use a sigmoid, I want to use a so-called ReLU function, I want to use a tan hyperbolic function, and then you would just pick the right function with its right derivative. So the derivative of that function, because this is now us taking the derivative of this function here, so that function, which is the example I'm going to use here. So if we do that, then this is going to be nothing but when we take the derivative of C of Cj of L multiplied with 1 minus sigma of Cj of L, which means that I have Aj of L multiplied with 1 minus Aj of L. So these are just some quantities which I need in order to set up the algorithm. So the next step, which I'm going to do now, when I'm performing thing, I'm going to now place myself at the output layer, because that's where I will now calculate the gradients from. So there is a reason why I don't calculate the gradients from the beginning. Could you think of that? So I'm starting the training of the gradients. You could start, why should I calculate the gradients from the input layer to the output layer? Why do I start at the output layer and go back? Any good reason for that? Yeah?
The weights that first there are having from the change from some change there.
Yeah.
That requires all the other layers for something else.
That's correct. That's a very good answer. And there's also another argument. Is often you have less output values than input values. So that means that the dimensionality of the output is smaller than the dimensionality of the input. Just think of a handwritten number from 0 to 10, you have only 10 outputs. Whereas you would start, if you have an image with 200 times 200 pixels, you would have 40,000 input variables. So clearly you would start where you have the smallest dimensionality. That's also a very important issue. But the one you mentioned is actually the more important. That's good. So let's now look what we are doing now. We place ourselves at the last layer. So we start at the output. So this is the output layer. And in our case, what we have then is the function of these parameters. So we have defined the function, the cost function, just to be the mean squared error. And this is now going to be given by the output from a node I minus the target value squared. So this AI of L is the output from node I in the last layer. So this is the output which our network produces. So we perform a feed-forward pass. So this is the same as that one. So when we do the feed-forward pass, what we have done now is simply that we have propagated all the values from X over here. These different nodes have weights and biases, which are set to a fixed value in the beginning. We can set random numbers. And then by performing these operations, we end up with a final output. And that final output is this one. And this is now where we start training a network, because now we have an output, we have calculated this quantity, and now we're going to take the gradient of that. So at the end, we would obviously like this, let's say the mean squared error, to be as small as possible. So this is a quantity we want to calculate. So if I do that, and I use the chain rule, and take the expression which we have here for the particular case of the mean squared error, what we get then is actually Aj of L minus this Tj. We get rid of the factor of 1/2 because we have from the chain rule derivative. So we have a dAj of L of d omega jk of L. Like that. I'm just using the chain rule now, right? Does that make sense? So everything is just applications of the chain rule. So when we then go back to those quantities which we put up, if you look at the quantities which we have here, so we will need them. So we actually put up this quantity, we have this quantity, and we also have that one. So we can now go back and set up the expression for that one. So if we now look at this dAj of L, of dWjk of L, this is nothing when we use the chain rule of dJl, of dZ, of JL. So I promise you, this is going to be an exciting exercise in the usage of the chain rule. You're going to love it. So these expressions here are those expressions which we put up just on the slide before. So we have the two expressions we need. We have this one, and we have this one. So we can just plug them back. And then what we get then is that this one becomes equal to aj of L of 1 minus aj of L multiplied with the previous layer with a node k of L minus 1. So I'm just using those expressions, which I had these helping expressions, to find this derivative using the chain rule. So I can then plug that back into the expression for the derivative of my cost function. So just keep in mind now that if you change cost function, clearly some of these expressions will change. And this is where automatic differentiation comes to a rescue, because then you can actually add more complicated cost functions and you don't need to bother about setting up the analytical expression for the derivatives. So that's, now you see immediately why automatic differentiation is useful. So if we bake this in, we take this in and plug it in here, then we have an expression for the cost function and its derivative at the final layer. So if we plug everything in, we have an AJL minus TJ, and then we have AJL. This follows from the derivative of the activation function we've chosen. So if we have a different activation function, we would have to change that. And then we have the next terms. So we would have that term and multiplied with an AK of L minus 1. There should be a minus 1 here. So let me just highlight some of these terms. So this comes from specific activation function. So if you have another activation function, you would simply have to calculate the derivative of that one. So that means that what we have here is the derivative of the activation function, Z, with respect. So if we now look at what we did here, this would be the derivative with respect to the input. So this is actually d of Z. I'm just writing it like that. So in case you have another activation function, you would simply just pick another derivative. And then also depending on the type of cost function you would have, you would also get a different derivative there. So that's why in the beginning, it's useful to actually do this by hand. So in the project, we are going to have a simple classification problem with a binary case and a simple regression case. And that means it's sufficient to actually plug in what we have here. But then you may have more complicated functions, and that's where gradient descent, automatic differentiation comes to rescue. And then we can actually simply bake in the expression for cost function and activation functions and let the automatic differentiation take care of these derivatives. So this is an expression we need, and it's common in the literature to actually define a new quantity. So what we have then is a quantity which we define as a J of L. And this is given in this specific case as AJ of L, or 1 minus AJ of L, multiplied with AJ of L minus TJ. And if we look closer at it, this would be the same as the derivative. I'm just writing it like that. The derivative of sigma, the activation function we've chosen. And this quantity here is in our case nothing but the derivative of the cost function with respect to the output in the final layer. So if we want to make classes and object-oriented our code, this is something which is useful to think of. If you're a little bit uncomfortable with classes, just write out the specific cost functions and just play around with that. Okay, so what we have now is an expression for these parameters. So I'm just going to write out these first derivative, dc at the final layer of L. And this is the same as this parameter, delta JL, and then multiplied with the output from the previous layer. So that's one of the derivatives we need. One thing which we can show, which I will leave as a small exercise to you guys, is actually to show that this dj of L can also be written out in terms of the bias. If I use the chain rule again. So it's all applications of the chain rule. And then I can show that this one gives me this gradient as well. It gives me the gradient of this unknown parameter B. So if I collect the quantities which I need now for this layer L, so if we now add to this the expression for delta J of L, so I would have F, this is the derivative of the activation function. So this should be a J, sigma, the derivative of CJL multiplied with the derivative of the cost function with respect to the output from that layer. So this would be the expressions which we need to get started. So these are the expressions for the derivatives. So we have an expression for the derivatives of the bias and a derivative for the weights, which are the unknown parameters. And this is just a simple exercise in chain rule and taking derivatives, when we have defined a cost function and a specific activation function. So what we need now is actually to propagate back, because now we have only the derivatives at the end point, but we have no idea about the values before. So remember now that when we initialize the first feed forward pass, we would set random values for the weights and the biases. And often you would choose them according to a normal distribution. That would be pretty common. You try to put small values so that the gradients won't explode. And then you would use these initial values to produce an output. So when you have the output, that's when you now start propagating back and training in order to find the parameters. So what we need now are actually these derivatives at a given layer L, which is not the output layer. So what about, and this is the final thing which we need, is a final expression. What about layer L? So let's set up these final expressions. So what we are going to do then, so we let now L go over to L, little l, which could be anyone. And what I need now is the following. So I'm going to set up delta J of L. This is the quantity I need. As you can see from the previous case here, this delta J of L is the quantity which is going to give us the derivatives of the weights at a given layer and the derivatives of the biases at a given layer. So what I need now is the derivative of the cost function with respect to this Z at a given layer L. And here again, I can use the chain rule. So I have a sum over the information from the previous layer. So I have a dck of L plus 1, and I have a dck of L plus 1, and then dcj at layer L. So I told you that the algorithm is just a repeated application of the chain rule. Now, next week, when we discuss automatic differentiation, you will see that this is exactly the same as reverse mode in automatic differentiation. But we will see these details next week. So when we do this, what we know then, so we know the value, this value here is something which we already have. We have it through the expression which you see here. So this delta J of L is something we can define from that. So we would then have simply a sum over k, and then I would have my delta k of L plus 1, and then so the previous value for this delta, and then I would have the derivative of zk of L plus 1 of dz of jl. Now, if I now look at the variable L plus 1, the input to node j in layer L plus 1, this is the same as the sum of I equal 1 up to NL, and then I have the weights, Ij, L plus 1, multiplied with the output from that specific layer, plus this Bj of L plus 1. So that means that when I take the derivative here, when you look at this expression, I need to take the derivative with respect to Zjl. So that means that what I will get then is that this dzk of L plus 1 of dzj of L is going to be equal to the weight kj of L plus 1. So that follows from this term here. But then, since I need also to take the derivative of that quantity, this is just the output from that specific layer. So this would be simply the derivative of the activation function with the input ZGL. So again, you can keep that general. And when you have a specific activation function, then you have a specific expression for its derivative. So it doesn't need to be the sigmoid function. So when I have this, I can now collect these expressions. And what I can do then is that I get the final expression for these parameters at a given layer, k of delta k, L plus 1, and then I have wkj, the weight, plus 1, and multiplied with the derivative of this activation function. And these are all quantities I can calculate. So next week, we're actually going to see how we implement this detail by detail so that you can follow the steps in the algorithm. So the equations, so we have 4 equations. So this is the final one. So we need that one. And when we have this equation here, we need the equations which you see here to kickstart everything. And when we have that, we can step back and calculate the update at every single layer. And what we will have then is actually that the gradients, which we are looking after, so when we are updating the parameters, we are going to need the gradients updates. So we are going to update the weights, WJKL, and that will receive as input, and this is nothing but the standard gradient descent algorithm, minus a learning rate, eta, and multiplied with a derivative, delta JL, multiplied with the output from the previous layer, L minus 1. And then I have the update for B's, the B's here, which will be Bj of L minus eta of the derivative of the cost function of Bjl. And this is nothing but the previous value minus the learning rate multiplied with this parameter JL. So this is going to be the update algorithm for the gradients, not for the values, not for the gradients. This is going to be the update algorithm for the unknown coefficients. And here we have the gradients, which are then multiplied with the learning rate. This is the equation which we are going to implement in order to train the parameters. So then the process, when you start with the output layer, after the first feed-forward pass, you move back to the first hidden layer. Then you have updated the weights and the biases for every single layer. And then you perform a new feed-forward pass. And then you go back and forth in a given number of iterations till, say, your cost function hasn't reached an ideal value. If you're doing the mean square error It should be 0. So let's set up the algorithm, because these are the equations which we will need to program. So the basic algorithm, it goes as follows. And this is where we will stop today. So you need to define the architecture, how many hidden layers you want to have, how many nodes you want to have, and what kind of activation functions. So you need to initialize the parameters W and B, so which we have collected in a container called theta. Define, so when I say define the architecture, that means also that you need to define, so this goes actually to the architecture, so define nodes, hidden layers, plus activation functions. You need to set up hyperparameters. You need to define them. You need to set up the learning rate. Plus gradient descent approximation. I just write gradient approximation. Whether you use Adam, Adagrad, just plain stochastic gradient descent, etc. You need to define the cost function. When you do a regression case, it is common that the output layer doesn't have an activation function. So that means that what you spit out as output for a regression problem is just a value. If you're doing a classification problem, you would often have a probability distribution, which you use as an activation function at the output layer. So these are things we will discuss in more detail next week. When you have this, then the next step is to obviously set up your data. So you set up X. So this could be the design matrix. And what you would do then is to find the first setup when you have initialized everything. Then you would perform the first feed-forward pass. Feed-forward. Because now you have all the information which is needed. And then continue to the last layer. So continue this to layer L. And essentially what you have then is that this A of L is now given by the activation function you have in that specific layer. And this contains information about the activation functions in the previous layer, and all the way down to the first layer, where this receives an input Z1. So you would have repeated matrix vector and matrix multiplications. That's essentially what goes on. And then you produce an output. And with that output, the next thing is that you would compute, when you come to the output layer, you now compute this quantity delta JL. So that's the first step. Then backpropagate. And when we backpropagate, we would then start with L equal L minus 1. You go to layer L minus 2, and this goes all the way down to the first layer. So layer 1. And then you would then calculate delta JL, which then is going to be given by the result from the previous layer. So you have a delta K of L plus 1 the weights from the previous layer, L plus 1, and then you have the derivative of the activation function in that specific layer. Normally, people keep the same activation functions, but you can change activation functions from layer to layer. Then, when you have that, the final thing you will do then is a training. So then you have the training element. So you get new weights and biases by simply using the gradient descent. So this is the gradient descent part. Gradient part. So I'm soon done. This is the last line. And I just wanted to set up the final step here because next week we will be discussing the way we can implement it. And then we have the biases. And then continue till convergence. And in most cases, convergence, in most cases, that means that if, for instance, if you have the mean squared error, you would like to drive that one to 0. And that's the mean squared error at the output layer. It's not the mean squared error in a given layer in the middle. Now, what you see here is that everything now is delicately dependent on the derivative of the activation function. So the training stops if the gradients are 0. So you don't want gradients to be 0. You don't want them to vanish. But you also don't want them to explode, because that will also mess up the training process which you have. So the training now is different from what you have in linear regression, where you're driving the gradients to 0. Here, you don't want to have them to 0. And it's a very delicate problem in neural network theory. And this problem is called either exploding gradients or vanishing gradients, because then the training stops. Okay? So this is the big picture, right? And next week, we are going to look at how we implement it. And hopefully then that can be a guideline for how you can set up your own code. I went a little bit over time, but I just wanted to set up the basic equations which we need to code. And what you see here is nothing but the application of a chain rule.